During Sonne Expedition 268, we're investigating the baseline for the ecosystem analysis, particularly manganese nodule habitats. This information is necessary to assess future potential mining and also test of equipment that will be done in the next few years against this baseline, so we get an idea of the impact of the mining operations. The primary goal of our project is to formulate suggestions for international regulations based on the scientific knowledge that we generate, and in particular for the mining code of the International Seabed Authority. This is unique because it is actually the first time that humanity is looking into the environmental impacts of its actions at the same time or even before it is starting to exploit the resource. At the moment, our knowledge about the deep sea, connectivity of species, so we know species exist across the Pacific, the same species, but we don't really know over which timescales they have this genetic exchange. For most of the species, we don't really know how fast they grow and how long they live. We have little information on what tolerance they have to changes in the environment, because even the changes in the deep sea, time series-wise, there is almost no information available. And that's one of the tricky things that we try to answer with our experiments, in situ experiments that we do in the seafloor and going there over several years, because the impacts could be larger than just the mining area. We have all important disciplines and experts on board to study the environmental impacts, starting with oceanography to measure bottom currents, resuspension of particles. We have a big array of sensors to investigate and measure and quantify the turbidity of sediment plumes when they are suspended during mining operations. We have biologists here for each faunal species and size classes, different experts, so that we can cover the range from small animals, myofauna, to bigger ones like holothurians that are 0.5 meter to 1 meter large, which are called megafauna. Then we have microbiologists here, because microbes are the key component in the ecosystem, producing nutrient fluxes from organic matter that they degrade in the sediment. And we have geochemists who look at these processes also on longer time scales of several thousands to even 100,000, maybe a million years in the upper few meters of the sediment. And then we have geologists looking at the bathymetry and the different sediment composition, so that we get a larger picture of these point measurements that we typically do into the area by analyzing the geological features. Basically every day we find something new species in all size classes, different environmental conditions. They are very variable. So the deep sea is anything but a plain, and this heterogeneity we need to figure out and better understand the processes of carbon cycling, how the deep sea ecosystem works, what its functions are, and in the end, as a coordinator of the project, what I like most about this job is actually putting together the information from all the different disciplines and come up with the holistic picture. And in this project, which is more applied, the nice thing is that that this helps the international community and regulators to be informed about the facts, and we can make suggestions for regulations to mitigate impacts from mining operations. Deep sea research, as we do it today, is technically really challenging because the deep sea, with high water pressures, 400 times the atmosphere, cold temperatures close to 0 degrees, is for the technology that we use and the gear very challenging, particularly when we depend on electronics. So it's anything else but a routine job to deploy this equipment. And you always have to live with bigger and smaller problems and even failures. Most of the technology we're actually deploying is not an industry standard yet, so we're really at the forefront of developing this deep sea technology, and that brings a lot of challenges during such a cruise.